Introduction and background. Why study microswimmers? What if we could have tiny artificial bacteria introduced into our bloodstream? What if we could have absolute control over them so that we could load them up with drugs to send them only to the disease ridden parts of our bodies, or with tiny cameras that can take an image of a faulty heart valve from the inside? These artificial microswimmers could non invasively clear a blood clot or deliver medicine directly to a tumor, in turn, reducing potential side effects and allowing for faster recovery. But swimming in the small scales inside biological fluids is not an easy feat, as biological fluids are complex non Newtonian fluids, and the physics of swimming is entirely different at this scale, where Reynolds number approaches zero. What we know. Analytical studies deriving equations of motion for bacterial swimming at this scale are valid only under conditions fitting the assumptions made in simplifying the governing equations. Pack-and-Laga's work describing the force of torque-free swimming of a bacterium with a rigid helical tail is based on the slender body and resistive force theories, which assumes the swimmer's tail is very thin and that the force and torque acting on the swimmer is a linear combination of its linear and angular velocity respectively. What is missing? These assumptions neglect the hydrodynamic interactions in the helical tail and between the tail and head, and all nonlinear effects. Their solution is only valid for Newtonian fluids, and an analytical model for bacterial swimming in shear thinning fluids does not exist. Our numerical study aims to fill these gaps by investigating bacterial swimming in shear thinning fluids. Solving for 3D Navier-Stokes equation with the shear rate-dependent Carew viscosity model, our simulations modeling the same swimmer used by Pack-and-Laga will be able to account for the hydrodynamic interactions and nonlinearities, as well as swimming in a shear-thinning fluid. CFD model, governing equations and validation. Newtonian. To accomplish this, we will first validate our simulation for the Newtonian case. When we non-dimensionalize the Navier-Stokes equation, the terms including time as a variable are scaled by the non-dimensional Reynolds number, which is the ratio of viscous forces to inertial forces. As the length scale diminishes, Reynolds number approaches zero, taking with it all terms involving time, and leaving the so-called Stokes equation. Time can now only enter the system as part of boundary conditions, which do not affect the flow field. Comparing our Newtonian simulation results with the analytical solutions from Pack-and-Laga at 3 different tail radii for a range of head sizes, represented as our head, we observe that both analytical and numerical results follow the same trend, and that there is an optimum head size that maximizes the swimming velocity for a given tail radius. Due to neglected hydrodynamic interactions and assumed linear relation, the analytical solution seems to overpredict swimming velocity. Shear thinning. Next, to extend our study to the shear thinning medium, we need to solve Navier-Stokes equations, taking shear-dependent viscosity into account, as the linear Stokes equation no longer applies. We chose the Carew fluid model as the literature shows that it captures the shear-dependent behavior of bodily fluids very well. The Carew model obeys the power law for intermediate shear rates, while it displays a near constant, Newtonian-like viscosity model at zero and infinite shear rate limits. Non-dimensionalizing the Carew constitutive equation, we found a relevant non-dimensional number called the Carew number, which is the ratio of the applied shear rate to the critical shear rate, the rate at which the shear-dependent viscosity reduction becomes prominent. When the shear thinning index is 1, which is the exponent in the power law region, solutions from the Carew model are expected to converge to the Newtonian solution, which is how we validated our shear thinning simulations. The results from the Newtonian model and the Carew model with a shear thinning index of 1 are identical. Results. Our results show that for a given tail radius, there is an optimum head size that maximizes the swimming velocity both when the fluid is Newtonian and shear thinning. Plotting the non-dimensional velocity versus the non-dimensional head size reveals that the same swimmer can swim faster or slower in a shear thinning fluid compared to swimming in a Newtonian fluid, depending on the head size and the shear thinning index. In other words, velocity is found to be a function of R head, Carew number, and shear thinning index n for a given tail radius. To isolate the effect of shear rate dependent viscosity reduction on the swimming velocity, we solve for the velocity over a range of different Carew numbers. For 3 different head sizes, where an increase in Carew number indicates a higher shear rate and consequently a lower viscosity fluid, We identified carrier number ranges and head sizes that result in enhanced or reduced swimming velocities, which indicate that designing a swimmer tuned for a desired swimming performance is possible. To explain our results, first we calculate the swimming velocity in shear thinning fluids over a range of carrier numbers and compare it to the Newtonian swimming efficiency. We define efficiency as the ratio of power used to generate translational motion to the total power consumed by the swimmer to translate while rotating. Consistent with previous findings of our research group, the helical tail is more efficient in a shear thinning medium compared to being in a Newtonian one. However, efficiency of the head is found to be dependent on the carrier number, which displays a similar behavior to the overall efficiency of the swimmer. Examining the viscosity maps revealed that the swimmer enjoys the so called soft viscosity effect when it is swimming at its highest velocity. The soft confinement effect emerges when the swimmer is swimming in a low viscosity region surrounded by a higher viscosity region, which effectively acts as a confinement. These confinements have been repeatedly reported to increase swimming speed in past literature. Future work. In order to fully explain the results, we next need to analyze the forces acting on the swimmer by isolating viscous and pressure forces. In future studies, we will also investigate the effect of rigid and flexible boundaries around the swimmer, as the circulatory systems and GI tract are networks of cylindrical channels which will contribute to the hydrodynamic interactions. We will extend our research to generalized helical swimmers by changing tail geometry and length. Ultimately, we will study microswimming in clusters and the effect that multiple swimmers will have on the hydrodynamic interactions and swimming trajectories. Finally, I would like to thank the Institute for Data Intelligent Systems and Computation for supporting this work with an undergraduate research grant. Thank you.